Okay, so we're left off with a velocity selector. Now when you have a charged particle moving through an area that has both an electric and a magnetic field, it can actually go straight through there, even though it's a charged particle in a magnetic field, by a couple things. By one, having the electric field, force of the electric field, balanced by the magnetic force. It doesn't mean the magnetic force is in the upward direction, that's the force of it. To balance out the electric force, that means that the velocity actually, that the magnetic field has to be actually into the page in this case. Alrighty, so we left off was right here, the velocity selector. So what you could do, if you're looking for a certain speed of particle for whatever reason, whatever experiment you're running, you can actually select what speed of charged particle you want by changing the electric field. If you made it stronger, well, that would mean that would mean the field is greater. That would mean that you're going to only collect faster particles. So if you want particles moving slower, you make this a little bit smaller, and then for the slower particles, because the force would be less from the magnetic field. Because remember, the magnetic field force depends on how fast they go. You could select out just certain speeds. Okay, so here we go. Determine the magnitude and direction of a magnetic field in such a way that a negatively charged particle. You see the negative? That's your left hand charged particle with initial velocity v. So I'm going to get my thumb in the direction of that velocity going this direction, and the field is downward for this thing. So that means the force is in what direction on it? Remember, it's a negatively charged particle. So if the field is down, the force is upward on the thing. The electric force is upward. So if I want to select out certain velocities, that must mean I need the magnetic force to be downward on this thing. So to have a downward force to balance that out, to make it go straight across through that, that means the magnetic field must be in what direction using my left hand to be downward? That's the next question. So what direction should this point to select out negative charges? It's going to have to be, force downward, it's going to have to be into the page. Okay, because remember, I'm using a negatively charged particle. So into the page for a negatively charged particle, because it's going to go the opposite direction, being an opposite charge there. All right, muy bien. Hey, so what happens in this charged particle? It's a large magnetic field, and we're going to call this a constant magnetic field. Pop quiz, guys. What direction is the magnetic field? Into the page. That's why you see the X's. Okay, so get out your right hand rule, because I think we're going to be a positively charged, because if it doesn't say otherwise, we're assuming it's a positive charge. So that must mean that it's going this direction, but the field is inward, so that means the force is towards the inside. So as this thing spins, so the force is towards the inside, so as this moves, now the force is downward, the field is still inward, now it's still towards the inside. So you notice as this thing turns, because the velocity is still perpendicular to the field, the force is still towards the inside, and what do you notice happening to this particle? It makes a loop. And how big that loop is depends on how massive the particle is, what the charge of the particle is, and how big that magnetic field is. So in other words, it's centripetal force. So we could actually put this thing in orbit in here and keep this going at a constant speed in a circle. So it's a circular motion, and there really isn't any work done. You might say, hey, why isn't there any work done? It's not changing speed. It's only changing direction. That's all the magnetic force can do. The magnetic force is not going to do any work on the thing. All the magnetic force does is change direction because it's perpendicular. So the magnetic field actually does no work. Electric field can do work, but the magnetic field doesn't do any work on the charged particles. It just causes the change in direction. So if you want to accelerate particles, you got to use an electric field to accelerate particles. But we use a magnetic field to turn them. So what the giant accelerator out there at CERN in Switzerland, they use magnetic fields to keep this thing changing directions as it goes in a circle. But they use an electric field to accelerate that thing. The magnetic field doesn't do any work. It's perpendicular. It just changes the direction of the thing. So now if you want to find out how big that R is, well, it depends on, like I talked about earlier, how big the mass is, how fast is it going, and how big is that field. Because if you remember, centripetal force is an mv squared over the R, and that force is actually the magnetic force that changes the direction. It's one and the same thing over here. So as we solve for, let's say if you want to solve for the r, how big the circle is, the r comes up, all that comes down below, and what do you end up with? You got an mv over q and b. So how big that curve is depends on the mass of the particle, how fast it's going, how big is the magnetic field, and what's the actual charge. So I'm going to give you a lab to do, which has to do with this stuff over here. So I click on this stuff to the right over here. Okay, and here we go. And I'll put this on later on. You can do a little lab and find out how big these little circles are here. Okay, so that's coming up in the future. Okay, we may have gone outside of our bound. I think we're still recording. Let's see if we can get back to our little slideshow. There we are. Or the other thing is, there's one more we're going to look at. And if I click this over here, this is a physics aviary once again. So we could fire this thing and find out how big of a curved path it is. And if you want to hit a certain point, what do you have to do to hit a certain point? Okay, so that's going to come up at a later time. So let's back over to here of how far where that thing's going to land. So by using this, we can determine exactly how much we curve. Or think of this. This is one way to separate particles by mass. So if you have a different charge, different particles, we could get them a certain velocity. And what happens is, and if they're all the same charge, more massive was like isotopes. So if you want to separate isotopes, so isotopes could have the same charge as another atom, but shoot them with their velocity. So, well, we get them to go in the same velocity, and the bigger masses do not turn as sharply. So we can collect masses or separate things based on mass, even if they have the same charge. As a use for that. All right, so here we go. Pre-flight 8.6. Each chamber is a unique magnetic field. Positive charge that enters at 75 meters per second straight up. What is the speed of the particle as it leaves chamber 2? Think about it. Think about it. First of all, how much work is done here? How much work is done here? The answer is no work. The magnetic field solely changes the direction. So they have to be the same velocity coming back out. The magnetic field doesn't do any work. It just simply guides the thing, changing the direction. So the magnetic force is always perpendicular to the velocity, so it changes direction, not the speed of a particle. All right, so now we have the particle coming in at 75. We have a charge, 25 millicoulombs. That's a good size charge. Oh my goodness. And follows that dash trajectory. Compare the magnitude of the field in chambers 1 and 2. Okay, so which one of these two would be a stronger magnetic field? Remember, the speed's not changing, and neither is the charge. So the bigger magnetic field has to be the one that bends the most. Okay? So we have the smaller r, that means it's a sharper turn. That must mean that the magnetic field has to be greater in 1 than number 2, because it's a sharper turn. That means a greater force. You could make a sharper curve, is what you could do. Okay, now we have a 75 meter per second particle. And hey, we don't know what this charge is, Dios mío. But we have a second particle, but we know it's twice the mass. Hits the chamber at 75, the same speed, and it follows the exact same path as the M1. Well, how could that happen? Well, it could happen by different charges. So what would be the charge of, because remember, the second particle follows the same path with the same mass as the M and charge of 25. So what is the charge of the one with the 2M? See, they have question marks. Oh, this is for the second one. So the original was 25. Alrighty, well, let's look at our equation here. So we have the exact same r because we have the same path. We have the same velocity, but we have the same magnetic field. So if one is a 2m, to make the same r, that means you have to have a 2q. Make sense? So to come in at the same speed, the same magnetic field, the exact same path, a 2m has to have twice the charge, and it'd make exactly the same curve because you'd have twice the force acting on the thing. Alrighty, so there you are. So that's what we have so far on the first set of magnetism. We have a second set following about the magnetic field around a wire, and more fun things with how do you make an electromagnet. All right, have a good one.